Okay, today we're looking at chapter 9J, minimum spanning trees. So we're going to break it down a little bit. So the first thing we need to look at is what is a tree? So we get a graph, okay, and a tree is a connected graph that contains no cycles, multiple edges, or loops. So they do look a little bit tree-like in these two examples. A tree may be part of a larger graph or a subgraph as well. That's a good point to make. So see with these trees here, they all connect, okay, it's all connected, but none of the vertices, or there aren't any cycles. So over here we've got a cycle here, that's why this one is in a tree. There's a loop here, which isn't good, and there are no multiple edges connecting the vertices. Okay, so these are things to look out for to see whether it's not a tree. A rule to tell whether it's a tree. So a tree will always have one less edge than number of vertices. Okay, so if you count the number of vertices, so that's what this n is, n, the number of vertices, okay, whatever that is, you minus 1 to find the edges. Okay, so if you've got 10 vertices, that means there is 10 minus 1 edges. And obviously 10 minus 1 is 9. So there are 9 edges if there are 10 vertices. Okay, that's for a tree. So if you look over here on the right, okay, we've got, this is a graph here. Okay, there is 5 vertices because we've got A, B, C, D, and E. Okay, at the moment it's not a tree, but to make it a tree, we need to have only 4 edges because our rule says we've got to have 5 minus 1 edges, so there are 4 edges. Okay, so this spanning tree could look different. There are different ways of getting it. So this tree here, okay, it's just gone around, so E, A, B, C, D. So it's still connecting all the vertices, but there's only one edge connecting each of them. So there aren't any cycles happening. Or another way you could do it is, yeah, D, E, A, and C, just like that. So a spanning tree connects every vertex using exactly one edge. So that's what we've done over here. There's only one edge connecting each vertice. As opposed to over here, so see B, it's got 3 edges which connect to B. So that's not a spanning tree. There are multiple options, which we've seen here with spanning tree 1 and 2. So we've looked at trees and we've looked at what a spanning tree is. Okay, it connects every vertex using one edge. So a minimum spanning tree, what that means is it relates to weighted graphs. Okay, weighted graph means that there's numbers assigned to the edges, which might be like distance, like kilometers, or it might be amount of money or something like that. The minimum spanning tree is the spanning tree of the minimum length, so we're always looking at the smallest way of getting somewhere, and there may be more than one. Okay, that's a minimum spanning tree. So there is an algorithm, Prim's algorithm, which is a set of rules to determine the minimum spanning tree. So to find the minimum, what you do is you choose a vertex to start from. Oh, well, hang on. What's happening? Sorry, guys. Okay, let me see if I can rub this. There we go. Okay, so back to Prim's algorithm. It's being weird. Okay, so to determine the minimum spanning tree, we choose a vertex to start from. Any will do. Okay, now from that vertex, you inspect the edges and choose the one with the lowest weight, so the lowest number. If there are two, so this little bit, if there are two with the same weight, it doesn't matter which one you choose. Then, once you're at that next vertice, you inspect the edges again to find the lowest weight, and then you've got 3 vertices connecting by 2 edges. So you repeat the process until all the vertices are connected, and then stop. The result is a minimum spanning tree. Calculate the length after. So if we go and have a look at this example here, okay, so we're starting at any vertice, and for this one we've chosen C. Okay, now looking at C, we need to go to the smallest, or go along the edge with the smallest weight or the lowest weight. So out of 8, 3 and 5, 3 is obviously the smallest, so we're going to go from C to D. So that's what we've done here, gone from C to D. Now from D, we look at the smallest one, so we've got 6, 5, 7 and 6. 5 is the smallest here, so we're going to go out to A. So now we're out at A, we need to go to either 2 or 6. 2 is the smallest, so we're going to go from A to B. Now, we're at a bit of a roadblock here, because now that we're at B, looking at the lowest weight, we would usually choose 6, but if we add these up, we've just made a cycle and we can't have that, okay? So we're going to stop here at the B, okay? And now we need to look at, well, we've still got to connect, we've still got E and F here to connect, okay? So what I would do is go back and have a look at the smallest numbers. So we could go from D, where there's a 6 and a 7, or we could go from C, which is a 5, which is the lowest. So we're going to go out from here, and it's going to keep it a tree because we haven't made a loop or a cycle or anything. And from the E to get to F, there's only one way, and we're going to go here. Okay, so it looks a bit messy, but over here on step 4, this is what we call our minimum spanning tree, and to finish we need to calculate the length. So that's what this is. We've added them all up, and there are 17 units, which is the smallest way.